All right, welcome to The Explainer. Today, we're going to build a super useful toolkit, one for measuring the space inside things. And trust me, by the end of this, you'll have the two key ideas you need to calculate pretty much any volume, and you'll definitely never look at an ice cream cone the same way again. So let's start with a really important question. But it's not just about ice cream, right? Think about it. How much coffee is actually in your mug? How much air is in the room you're in right now? All of these questions, they're all about one simple concept: volume.
Okay, so what is volume, really? Well, simply put, it's just the amount of 3D space something occupies. A good way to think about it is, imagine you could fill any object with water. The amount of water it holds, that's its volume. It's all about the inside.
All right, let's get into it. Our first group of shapes, I like to call them the stacking shapes. You'll see why in a second. These are the ones built with straight, parallel sides.
So the big idea here is something called a uniform cross-section. And it's way simpler than it sounds. Think about a loaf of bread, right? No matter where you slice it, every single slice is the same shape and size. That's exactly what's going on with these shapes. If you could slice through them anywhere, the new face you create would always be identical.
And here's the best part, the really elegant bit. There is one simple formula that works for every single one of these shapes. All you have to do is find the area of that repeating shape, that cross-section, and multiply it by the height. Seriously, that's it.
You know, the easiest way to picture this is to think about stacking. Imagine a stack of coins. What's its volume? Well, it's just the area of a single coin, right? And you just multiply that by how high the stack is. Our formula, it's just the math way of saying exactly that.
And you can see just how powerful this is. Take the cuboid. Its base is a rectangle, so the area is just length times width. You multiply that by the height, bam, you've got the volume. Now look at the cylinder. Its base is a circle, area is pi r squared, multiply that by the height, and you get the volume. See? It's the exact same logic. The only thing that changes is the shape of the base.
Okay, so this stacking idea is fantastic for anything with straight sides. But what about shapes that don't stack so neatly? What happens when the sides all come together at a single point? Yeah, for that we're going to need a little addition to our toolkit. And that, of course, brings us to our pointy shapes. Pyramids and cones. They've all got a flat base, sure, but then all the sides rise up to meet at a single point at the top, the apex. This means our stacking logic, well, it needs a small but really important adjustment.
Now just look at the formula for a second. See how it looks super familiar? It's almost the same as the one for prisms. You still got the base area, you're still multiplying by the height, but there's one little thing added right at the beginning.
It's this little guy right here, 1/3. It's kind of amazing, actually. Any shape that goes from a flat base to a sharp point has exactly 1/3 the volume of a prism with the same base and height. That's it. That's the magic number. It's the only new piece of the puzzle you have to remember.
And yep, you guessed it, this rule works perfectly for cones too. I mean, what is a cone? It's basically just a pyramid that happens to have a circular base. So the formula is identical. 1/3 times the area of that circular base times the height. The logic holds up perfectly.
So now we have these two core formulas, which is awesome. But we can do more than just find the volume. We can actually use them to work backwards, kind of like a detective, to find missing pieces of the puzzle. All right, let's try one. Look at this cone. We're told the volume is 1,000 cubic centimeters, and we know the radius is 7. But the height, well, the height is a mystery. It's labeled x. So the question is, how in the world do we figure out what x is? Well, it's actually pretty straightforward. We start with the tool we already have, our formula for the volume of a cone. Then we just plug in the numbers we know, the volume and the radius. The only thing left in the equation is our mystery letter x. From there, it's just a little bit of algebra to get x by itself. See? The formula isn't just a one-way street.
All right, let's do a quick recap. Let's pull everything together and look at the two essential rules we've just put in our volume toolkit.
You know, it all boils down to two simple questions. First, does the shape have straight, parallel sides, like a stack? If yes, its volume is just the base area times the height. Second, does it come to a single point? If yes, you just do the same thing, but multiply it by 1/3. That is literally the entire toolkit right there. Okay, so now you have the tools, which brings us to the final challenge. Take a look at this shape. How would you even begin to find the volume of this? How could you break it down using the tools we just talked about? What parts would you calculate, and how would you put them all back together? I'll leave you with that one to think about.